Hello, welcome to Magnolics Conference. My name is Thibaut Devolder. I am from the Centre de Nanosciences et Nanotechnologies. This is in Université Paris-Saclay in France. And I have the honor to show you the first tutorial of this conference, which is about the electrical methods that we can use for the study of spin-wave dynamics. Most of my talk will be about a method that is called propagating spin-wave spectroscopy that was pioneered by Mathieu Bayeul and co-workers exactly 20 years ago. To implement propagating spin-wave spectroscopy, you need two things. First, you need a magnet that hosts the spin waves that you want to study. And second, you need a vector network analyzer. The first thing you do is you want to have some control on the magnetization of your sample. So you generally apply some strong magnetic field, strong or weak, whatever it is. Then, on your magnet, you pattern radio frequency antennas, and you flow RF current in these antennas from the vector network analyzer. So this generates locally RF magnetic fields below the antenna so that you excite magnetization dynamics, and spin waves will propagate away from the antenna. You let them propagate, and you collect the corresponding signals with a receiving antenna. That's the idea beyond propagating spin-wave spectroscopy. If you look at the scientific literature, you'll find plenty of shapes of the antenna. Coplanar waveguides, single wires, U-shaped antenna, meander-shaped antennas, so very many shapes of antennas. And the reason is that people that want to study spin-wave dynamics, they want to control the wave vector content of the spin-wave wave packets that they generate. And the best way to engineer the wave vectors is to have proper shapes of antennas. But in any cases, what they record is the transmission coefficient between one antenna and another, and it yields transmission spectrum that are typically like that. Here you have a transmission spectrum versus frequency. It's a transmission coefficient, so it has a real and imaginary part. And my goal today is to explain you why we have such kinds of spectra, what is the information that is contained inside the spectra, and how we can extract this information in a reliable manner. So this is the outline of my talk. I will first revisit a problem that is apparently simple, which is how a given RF antenna excites spin waves. Then I will go to the reverse problem and study how the same antenna can detect the stray field and the inductive signal coming from the spin waves. Then I will try to see what happens during emission of spin waves at one antenna and collection of the spin wave at a distant antenna. So what is the effect of propagation? And finally, in the last part of my talk, I will discuss the importance of the dispersion relation of the spin waves. So let's start by an apparently simple problem, is that how an inductive antenna excites magnetization dynamics in spin waves. All along this talk, I will consider antennas that are infinitely long. That is to say, the antenna here, I plot the cross-section, I draw the cross-section. The antenna runs infinitely in the direction perpendicular to your screen. And the first thing that you have to ask yourself when you fabricate a sample is whether you want to have the antenna on top of the film or below the film. And this first choice has its importance. Let me explain why. If you flow an RF current inside the antenna, it will generate essentially in-plane fields below and above the antenna, and out-of-plane fields also below and above the antenna. And if your film is above the antenna, it will see a positive RF field pointing to the right, and either a negative or a positive fields, out-of-plane field, depending on where you are exactly. But what happens if you reverse the position and you are below the antenna is you reverse the in-plane fields, the blue arrows, but you do not reverse the out-of-plane fields, which are the red arrows. So you do have a complicated spatial profile of the RF field generated by the antenna, but if you're above or below the antenna, you have the same out-of-plane field, but a different in-plane RF fields. So you immediately see that if your sample responds to these two field components, in one situation they may help each other, while in the other situation they may have opposite effects on the magnetization and either completely or partially cancel. Okay, so what is called helicity mismatch, and that I will discuss later on, depends on the position of the antenna with respect to the magnetic field you're studying. The second thing that is important and that you have to realize is that it depends on the sign of the wave vector. So let's still have this antenna that is on top of the magnetic field, okay, and say that this antenna generates an in-plane field and an out-of-plane field in red. So a circulating RF field. Now imagine you have your film, I'm showing a cross-section, and the film hosts the spin waves. So the spin waves has dynamical magnetization components of two types, in-plane components in blue, and out-of-plane components in red, and they rotate in space because it's a wave. And here I've chosen a situation where I take a snapshot of the magnetization of the spin wave at some time, and I've taken a snapshot at a time when the RF field of the antenna, here in green, is parallel to the dynamic magnetization of the spin wave everywhere in space. And this is for a positive wave vector. So at this time, at this specific time, the angle between the RF field and the dynamic magnetization is uniform in space. If now you wait a quarter of period, what happens is that the spin wave advances, and while it advances, the RF field of the antenna goes to zero because you have an AC current in the antenna. And if you wait another quarter of period, the spin wave still advances, but now the RF field of the antenna has reverse direction. But still, with this wave vector direction, the dynamic magnetization and the RF field still makes the same angle as in the beginning. In this drawing, they are parallel. So you can see that the two components of the magnetization will feel a torque that is in phase. If in contrast, instead of using a wave vector pointing to the right, you use a wave vector pointing to the left, then in this case you can see that at any snapshot in time there will be in-plane, you will have either the in-plane component of the magnetization or the out-of-plane component, which will be out of phase with the exciting field from this antenna. So you will see that for this sign of wave vector, now the two field components of the antenna do not help each other to excite the magnetization dynamics. And that's what we call helicity mismatch. So it means that the helicity of the electromagnetic field radiated by the antenna either matches with the helicity of the spin wave or it doesn't match. And this will yield to different excitation efficiency of the spin waves. So you see that in the excitation problem, you have to consider the position of the antenna with respect to the field, whether it's above or below. So you'll have sine of z, where z is the position of the antenna, and also whether you're considering spin waves with positive wave vectors or negative wave vectors. So in any criterion for excitation of the spin wave, you will have terms that are like that, sine of k times sine of t. So that was how you could see the helicity mismatch in real space. Let's now look at it in reciprocal space, because when we deal with waves, it's very often much more practical to look at them in reciprocal space. So that was the spatial profile of the in-plane field below the antenna in real space. You can see that it's a real function, of course, it's a field, and it's even versus horizontal position. So this, since it's in real space, it's a real and even function. In reciprocal space, it will also be a real and even function, but now of the horizontal wave vector. So if you only look at the in-plane component of the field generated by the antenna, you see that it's an even function, so plus k and minus k play the same role, and they will have similar effects on the magnetization. In contrast, if you look at the out-of-plane component of the field generated by the antenna, then you see that now, of course, it's still a real function, it's a magnetic field, but it's now odd versus horizontal distance. So if you go to reciprocal space, it will be an imaginary function which is odd in horizontal wave vector. And the spectrum of the out-of-plane field versus wave vector is indeed an odd function. So now you see that while for the in-plane field generated by the antenna, plus k and minus k were similar, here you can see that plus k and minus k are different and opposite if you consider the out-of-plane field generated by the antenna. So you see that this is still helicity mismatch, that is to say that the sign of the wave vector will be important because it will change whether the out-of-plane components and the in-plane components work against each other or work together. By the way, notice that the two spectra for the out-of-plane field and for the in-plane field, they just differ by a phase factor, so they contain exactly the same power. Let's go further in that direction and imagine we're using complicated antennas. Okay, so far I've been dealing with an antenna of rectangular cross-section, so it yields a given spatial profile and a given reciprocal space profile, and you can express them analytically on this geometry, but these are complicated functions of the spatial coordinates and of the geometry of the antenna. And you don't want to see these complicated functions. But hopefully, we're working with a 2D geometry. That is to say that the antenna runs infinitely in the direction perpendicular to your screen. Okay. So you can use these properties and apply Maxwell's equations. And what you will see is that in fact, you have symmetries in the system. Okay. And even if you use an antenna that has a complicated shape, for instance, instead of using a rectangular antenna, you use an antenna that has the shape that combines a shoe and a bat. So any random shape, but still a 2D problem invariant in the direction perpendicular to your screen. Okay. Then because Maxwell's equations are, of course, apply, okay, you will have that the spectrum of the in-plane field and the spectrum of the out-of-plane field are effectively very similar. They just differ by a phase factor, a phase rotation of pi over 2 in reciprocal space, and the sign of the wave vector. And this is very important, okay, because when you use inductive antennas, you don't really have to care about the exact shape of your antenna, whether the current is uniform in the antenna or not. Okay, because in any case, you know you will generate two components of RF field. They will have the same power. They will differ by a phase factor, and this phase factor depends on the sign of k. Okay, so let's now forget about the shape of the antenna, the exact shape, and use this property. Okay. So summarizing, the RF field seen in reciprocal space has an in-plane and out-of-plane component. They may have amplitudes that are complicated to express, but these two components, out-of-plane and in-planes, are not independent from each other. Okay. Well, this was when the antenna was running in the direction perpendicular to your screen. Now what we can do is we can rotate the antenna, or equivalently, we can rotate the magnetization of your magnet that hosts your spin wave system. So when you do that, so you rotate the antenna, but the antenna is still infinite, what happens is that if you rotate about the z direction, then of course the z field doesn't change. Okay. But the in-plane field, the blue component, okay, you have to look at it in the directions transverse to the magnetization. And then as you rotate your magnetization, or as you rotate this antenna, the amplitude of this RF field that is sensed by the magnetic system varies, okay, in a sinusoidal manner. And this is important because if you start from the usual situation, so the most used situation is the Damonesh bar situation, where you have the magnetization of your film that runs parallel to the antenna. So that's the cross section. And in the top view, you would have the magnetization running parallel to the antenna. And you're considering a wave vector for the spin waves that are radiated away from the antenna. If you look at this situation, you can see that the torque that is supplied by the antenna fields to the DC magnetization, it's a torque that rotates in space, and it's a circularly polarized torque. And once again, this torque matches with the spin wave helicity, and you have helicity mismatch. It's still the same phenomenon. So that was for the Damonesh bar configuration when the wave vector was perpendicular to the magnetization. If we want to express that mathematically, okay, of course what you need to write is the exact susceptibility of the magnetic sample times the RF field, and this gives you the dynamic magnetization. So the susceptibility is a tensor that you can write in a 2x2 tensor in the plane transverse to the magnetization, with diagonal components that are what they are, okay, and anti-diagonal components that are offset by a phase factor of pi, and that express the helicity of the spin wave, of the precession of the magnetization. And so if you look at the response, okay, in fact you find that the amplitude of the response is 1 plus epsilon, where epsilon is the helicity of the precession, times a vector that expresses the fact that in-plane and out-of-plane components of the magnetization are proportional to each other but dephased by pi over 2 because it's precession. Let's now go to another situation where instead of adding the field in that direction, we rotate the field and we go, for instance, to the backward volume configuration, where now the magnetization is parallel to the wave vector. So you have your magnetization here in green and still the field from the antenna in red and blue. And what you can see is that the torque, there are some positions at which you have no torque, simply because the magnetization is parallel to the RF field. So you now have a torque that is linearly polarized in space, while of course the precession of the magnetization is still circular. So you want to excite circular precession with a linearly polarized torque, and this is not that efficient. You have a tiny response, okay? And it's because you have this tiny response that many people don't like this backward volume geometry. That is difficult where it's difficult to excite magnetization dynamics. If you do the math, what happens, the only thing you have to change is that the RF field is now rotated with respect to the antenna. So you multiply this one by the cosine of pi over 2, which is 0, okay, so that you still have a response that is the precession of the magnetization, but now with an amplitude that is much smaller, okay, and related to the helicity of the precession. Okay, so that was the two usual configuration, Damonesh bar and backward volume. If now you go to an intermediate angle, okay, that is to say you put the magnetization at some angle phi with respect to the wave vector, then now the RF field of the antenna is no longer 1 and I, or 0 and I, it's sinus phi and I. So that if you calculate the RF magnetization, you will have an amplitude and still a precession of the magnetization. But you can see that if you select in a clever manner the angle of the magnetization with respect to the antenna, the amplitude of the response can vanish. It can vanish for a given wave vector, or for a given wave vector direction. If you use the other wave vector direction, it doesn't vanish. So you end up in a very interesting situation where you've selected an angle, okay? And in fact, you can be in a situation where it's impossible to excite positive wave vectors, and it's possible to excite negative wave vectors. So if you do that, you've successfully only excited K positive spin waves in this configuration. And this is important because it means that by playing on the helicity mismatch, you can go to a situation of perfect helicity mismatch where you do not excite one side of the wave vectors. So this ends my section about how an antenna can excite spin wave dynamics. Okay, and what I want you to remember is that in fact it's simple if you look at it in the reciprocal space. I now go to the second part, which is how the same antenna can detect a spin wave. And for this we have to examine what is the stray field that a spin wave generates. So imagine we are still in a Damon-Eshbar configuration, that is to say the magnetization is pointing towards you, okay? And the dynamic magnetization of the spin waves here is still the red and blue arrows that rotate in space. So here it's plotted for a circular precession. And we have to ask ourselves, what is the stray field that these spin waves generate? For this, we first look at the stray field generated by the blue spins here. And you can see that here, if the magnetization points to the left, the stray field will point to the right. While if we look at the stray field of the red spins, here you will see that they generate a stray field that points to the left. So you can see that here, above the film, the stray field generated by the two components of the dynamic magnetization cancels. They are in opposite directions on top of the film. Okay, if in contrast you look at the bottom of the field, so this is the same spin wave, the same geometry, but now you look at the bottom of the field, you see that the field generated by the blue spins points to the right, and the field generated by the red spins points also to the right. So now they are adding. So you can see that you are in a situation where, because you have a spin wave in your film, there is one side of the film which is a dark side where you have a low stray field, and another one where you have a high stray field. And this was for positive K vector. If you make the same drawing for negative wave vectors, what you will see is that the stray field, the high stray field side and the low stray field side get inverted. Okay, and so they get inverted. And in fact, this is a situation that you all know, because I guess at your home you have fridge magnets. And fridge magnets, if you use them, you know that they stick on the good side, they stick on the fridge. But if you reverse the side of your fridge magnet, you can try to stick it on the fridge. It doesn't work at all. And the reason is, the magnetic domains inside your fridge magnet, they are rotating in space, just like a spin wave. Okay. And they rotate in space in such a way that you have a double flux on one side and no flux exiting from the fridge magnet on the other side. So it's a single-sided stray field. It sticks on one side only. And the spin wave is also a rotating magnetization pattern which rotates in space. And that's the reason why you have a high stray field side and a low stray field side. Of course, you can write that mathematically, okay? And then you will see that the stray field related to the spin wave on top of the film at a position z, okay, it decays exponentially when you in the z direction. It rotates in a cosine-like, sine-like fashion in the direction of the wave vector. And it has an amplitude that is related to the Fourier component of the dynamic magnetization, with once again sine of k and sine of z. As I told you, there is a high stray field side, so sine of z, and it reverses when you reverse the sine of k. Okay. Well, but now it's a spin wave. It's not domains, okay? And the spin waves, you have a link between the out-of-plane component of the magnetization and the in-plane component of the magnetization. And this link is simply that they're dephased by pi over 2, that their amplitudes differ by the helicity of the precession, the ellipticity of the precession. So these two components in Fourier space, they are not independent. And just like before, when you were rotating the magnetization with respect to the antenna, you can rotate this magnetization if you rotate the wave vector. Okay. And if you rotate the wave vector, you will be able to tune the in-plane component of the magnetization seen by the antenna. So there's two interesting situations. One interesting situation is when your spin wave is exactly like a fridge magnet. That is to say, the helicity of the precession, the ellipticity, is exactly 1. Okay? And in this case, the spin wave generates no inductive signal on top of the film, and it generates an inductive signal below the film. Okay, but this depends on your magnet, and you may not be able to have a magnet with an ellipticity of the precession that is 1. But the other choice is to rotate the magnetization with respect to the antenna, so that you reduce this component by sine of phi. And in this case, you will see that you can select an angle so that the spin wave is seen like a fridge magnet, okay, and doesn't emit stray field. So in this case, the antenna doesn't see the spin wave, doesn't see an inductive signal. So let's say this spin wave is dark to the antenna. And of course, you know reciprocity. And it's somehow logical, because it's the same angle that we identified before that was leading to no excitability of the spin wave by the antenna. And it leads us to the intuitive conclusion that if you have an antenna that cannot excite a spin wave, it can also not detect inductively the spin wave. And this is what happens for this angle, that is the angle for perfect helicity mismatch, or the angle for no inductive detection, which are, in fact, the two same phenomena. And this brings me to the end of my second part. And the main message here is that a spin wave is a fridge magnet, has a dark side and a bright side. And we come back now to propagating spin wave spectroscopy, where not only we want to excite and detect the spin waves, but we also want to know how propagation affects these spin waves. So I will oversimplify the problem in this tutorial and assume that the antenna generates only an in-plane field and that the magnetization only responds in the in-plane direction, and it's just to make the math easier for this tutorial. So first thing you have to ask yourself is whether the antenna will excite spin waves, okay, and it will excite spin waves. It needs to satisfy two conditions. The first of them is the antenna should emit at the proper wave vectors. So this here is the Fourier component of the antenna field, so the antenna efficiency function. And you need the spin waves to be excitable, so to have a decent susceptibility with respect to this applied area. And you will see that the reflection coefficient of the antenna is finite, provided the antenna excites the proper wave vector and provided the spin wave responds to this wave vector. So a very common situation is when you have a macroscopic antenna, so a very wide antenna, and for instance you're doing a VNA FMR measurement. So in this case you only excite k equal to 0, such that the reflection coefficient of the antenna, okay, is simply the susceptibility of the resonant wave vector, which is k equal to 0. So that's why in VNA fMR signals, you have signals with real and imaginary parts that are meant to mimic the susceptibility of your film at 0 wave vector. But when you do propagating spin wave spectroscopy, you're not using a macroscopic antenna because you want to excite finite wave vectors. So you use a small antenna so that the wave vectors that you excite span from 0 to something like the inverse of the antenna size. So not only you excite the k equal to 0 spin waves, but you also excite higher k values with some efficiency that will depend on the excitation spectrum of your antenna. So that instead of having a response that is peaked at the fMR frequency, you integrate over all k vectors and you have a reflection coefficient which is a function like that, which is 0 in the spin wave gap, non-zero when the density of states of spin waves is non-zero and the antenna is efficient, and when you go to high frequency, this means also high wave vectors, then the antenna starts to be inefficient. So you somehow have an envelope in frequency domain in which you can excite spin waves, and you can see that in the reflection coefficient of the antenna. Okay, but then it only tells you whether you excited spin waves or not. It doesn't tell you what happens to the spin wave. So to see what happens to the spin wave, you need to let them propagate. And so you will look at the transmission coefficient, the S21 or the S12 of your VNA. And then there's an additional factor in the response of the system is that not only you need to excite the spin waves with the antenna, excitation being proportional to the susceptibility, but the antenna, the spin waves will propagate at a distance r between the two antennas, and they will phase rotate according to their k vector, which is linked to the frequency by the dispersion relation. So while in reflection you just had an envelope that told you, okay, these spin waves are excited, in the transmission coefficient you will have propagation-induced dephasing, so that you will have transmission spectra that look like that, where in addition you have phase information because each spin wave that is generated has a phase that rotates upon propagating between these two antennas. And so you immediately see that in propagating spin wave spectroscopy, you need to phase analyze your transmission coefficient, and this will help you to demultiplex the k values that you've excited. And you can make simple assumptions that the damping in your system is small, that the antenna is small compared to the attenuations of the spin waves, and you expect a signal that looks typically like that, transmission coefficient, which is scalar numbers related to the antenna efficiency and the loss and the propagation loss of the spin waves, and a single complex number that contains the information about the k vector. So you expect to have transmission spectrum like that, with an envelope that is related to the antenna shape, and a rotation in frequency, okay, with complex and imaginary, real and imaginary values, that just tells you this phase rotation operator. Okay, so this ends my part about what happens if you are in a simple situation and you can assume that there's a single family of spin waves in your system. Most often it's not the case, and while you try to excite a given spin wave family, you will also excite other spin waves, okay? And they are in the system, they propagate, and you will collect them, and you have to understand what they do also. So far there was a single spin wave family in your system, okay, so let's say the Damon-Hirschbauer mode quantized in the widths of your antenna. And indeed, we were expecting an envelope transmission with a phase rotation inside, and in some situation, for instance, a 5 micron wide cobalt-iron boron conduit, you indeed have spectra that looks like that. But in other situations, for instance, if you reduce the dimensions and you have quantized modes, okay, they will be quantized in the width and they will propagate along the lengths of your spin wave conduit, then your transmission coefficient contains the sum of the contribution from several spin wave families, which is potentially complicated. And just as an example, imagine you use a simple system, so a 1 micron wide spin wave conduit made of cobalt iron boron, 30 nanometer in thickness, then the transmission spectrum looks like that. Okay, and good luck if you want to fit this kind of spectra with this kind of model that only considers one family of spin waves. In fact, what you have to do is to find the way in which you will treat this spectrum to identify the contributions of each spin wave families that is present in your cell. Okay. And in fact, this can be done electrically. Let me remind you that when you record a transmission spectrum, so versus frequency, what you do is you apply successively one frequency, the next frequency, the next frequency to reconstruct this spectrum one by one. And in the end, the information that you have is the transmission spectrum of spin wave from 0 frequency to infinite frequency, or frequencies that are high enough so that no spin waves contribute to the signal. So from 0 frequency to infinite frequency, let's say. And you know that if you have a linear system and you know the response, the complex response at every frequency, you can know the response to every time domain stimulus. And this is a classical problem in electrical engineering. You describe your transfer function of your filter, phase and amplitude, and if you know the transfer function of your filter, you can calculate the response to any time domain signal that you're sending to your filter. And we can do the same for the spin waves. We can take the frequency domain data and calculate the response to any time domain stimulus. Okay. And for instance, you can calculate the impulse response, that is to say, the Gedanken experiment, where you would send a very strong and very short magnetic pulse at the emitter antenna, excite magnetization dynamics, and have an oscilloscope connected to your receiving antenna, and the oscilloscope would record the magnetic signal arriving after the initial impulse excitation. And so this is exactly the same data, but plotted in time domain. And if you do that, what you will have is you will plot the impulse response versus the travel time of the spin waves. And for instance, if you wait for this spectrum, if you wait 1 nanosecond, you will see a wave packet of spin waves arriving, which means that once you hit the emitter antenna, it takes them 1 nanosecond to go to the receiving antenna. Okay, so these are fast spin waves. But if you're patient, you will also see slow spin waves, so these turtle spin waves, arriving later because they are not so fast. And if you are very, very, very patient, you will see snail spin waves arriving a few nanoseconds after, because these are very slow. So you see that these are exactly the same data as in the spectrum, but in the spectrum, you see phase rotation plus some complex stuff here, okay? But if you look at them in time domain, then you can select the spin waves and see that they arrive at different travel times depending on their velocity. So you're been organizing a race of spin waves in your system to separate the fast spin waves from the slow spin waves. Okay, but then what can you do with that? The good thing is that when they are separated, you can make time-of-flight spectroscopy. That is to say, you can select the first wave packet, the fast spin waves, and calculate the corresponding transmission signal, the corresponding transmission spectrum that would be if there was only these families of spin waves. You can do that also for the medium velocity spin waves and for the slow velocity spin waves. But you can do more, because in fact, the frequency domain spectrum contains the signal of the spin waves, these three families of spin waves. It also contains noise, and it also contains electromagnetic feed-through, that is to say a direct coupling between the input and the output antenna. This direct coupling is capacitoinductive, so it propagates at the speed of light. So it's responsible for the signal that arrives at very small travel times. So by just removing the power arriving at small travel times, you will reduce a lot of the electromagnetic crosstalk. And also for the noise can arrive together with the spin waves, but it can also arrive before, after, and much after. Okay. So if in your spectrum you make it in time domain, okay, you can see, for instance, that probably anything that arrives after 20 nanoseconds is just noise. So you can find the spectra of all these components separately, the one of electromagnetic waves, the ones of spin waves, and the one of noise. If you look at the ones from the spin wave, and for instance, if I select the fastest spin waves, here the horse family, and I back calculate in frequency domain their corresponding spectrum, you can see that now the spectrum very much looks like what you would expect for a single family of spin waves. And it's the same if I take the turtle spin waves. They now lead to a spectrum that matches with the single family spin waves, and also for the snail spin waves. Okay, by the way, the amplitude here has been multiplied. Okay, and so you can, for each of these velocity selective spectra, you can unwrap the face of the transmission coefficient, get the wave vector, and have the dispersion relation for each of the family of spin waves. And this is, for instance, for the Damon-Eshbar family, okay, not quantized in the film, or the first quantized level, versus wave vector. And the bold line is what the dispersion relation that comes out from these horse spin waves. And the faint line is the theory. And you can see, without any adjusting parameter, and you can see that effectively, by organizing a race between the different spin waves, you can find the dispersion relations of each of the families present in your system. And this ends the part of my talk that is related to the propagation of spin waves. And in the last part, I want to emphasize that the dispersion relation, the exact shape of it, is important. And implicitly, so far, I've considered spin waves that have an even dispersion relation. Let's say V-shaped, like Damon-Eshbar waves or forward waves. But this is not the only situation that arises, and in fact, in many cases, the dispersion relation is not like that. And for that, I want to give you an example, and I will examine a multilayer. So we come back, before examining a multilayer, we come back to the single layer case. Okay. Imagine you still have a wave vector propagating to the right in a Damon-Eshbar configuration with dynamic magnetizations of the spin wave drawn as these red and blue arrows. You remember that the stray field above and the stray fields below are different. You have a high stray field side, low stray field side, and these sides are swapped when you change the sign of the wave vector, like a fridge magnet, once again. Now, for a multilayer, the situation is that you have several films, and each of these films generates a stray field to the other layer that is either on the high stray field side or on the low stray field side. So if you are in the first situation where the two stray field sides are overlap, okay, so it means you have your two fridge magnets in front of them, then what happens is that they attract each other. Okay. So the dipolar coupling reduces the energy of the spin wave in the system compared to the spin wave in a single layer case. If on the other end you are in a reverse situation where the two films are such that their low stray field size are in front of each other, just like if you had two fridge magnets facing opposite to each other, then they do not interact because they don't have stray fields. So what you can see is that if you start from a single layer with a V-shaped dispersion relation, for negative wave vectors, there is no dipolar coupling between the two layers, so the spin waves of the coupled system has approximately the same frequency as the single layer, but on the other case, because there is this dipolar interaction that reduces the energy, you reduce the energy of the system, and you will end up in a situation that is non-reciprocal, where the frequency of a spin wave with positive wave vector will not be the same as with negative wave vector. So non-reciprocity. And I want to emphasize that when you have multi-layers, you have dipolar coupling between the layers. And so the general situation is that the dispersion relation of a spin waves in a complicated system will be non-reciprocal. That's an example taken from the literature, from the paper of Quinn and co-workers. For instance, in their case, they have an isolated YIG film, so a single layer. You can see that the dispersion relation is V-shaped. But if they make a bilayer, YIG plus cobalt iron boron, you see that because of the dipolar coupling, the dispersion relations now starts to be very non-symmetrical. Okay, just like here in my drawing. So non-reciprocity is the standard situation. Okay, so let me cast the dispersion relations schematically in three categories. V-shaped dispersion relations that has been studied for years in the Damon-Eshbar situation, but there are many others. Sorry for the typo here. Then there are other situations in which the dispersion relation is quasi-flat. That's, for instance, in the backward volume situation where the slope, it's not flat, but slope is small. This is not so interesting for propagating spin wave spectroscopy because since the group velocity is low, the spin waves die out before they reach the receiving antenna because it takes them a lot of time, if they are slow, to arrive at the destination, and they are damped before arriving at destination. But there's a very interesting situation, which is when the dispersion relation is monotonic. And this happens in many bilayers or in synthetic antiferromagnet magnets, especially when you have wave vector parallel to the applied field. Okay. And so I will assume this for a start, that we have this kind of dispersion relation, line-shaped, and I will assume that the susceptibility of the sample is very simple, just for didactic reasons during these tutorials. So if we do that, okay, what is interesting is that since the dispersion relation is monotonic, if you excite a wave packet of spin waves, so with both negative wave vectors and positive wave vectors, whatever the wave vector, the slope is positive, so the group velocity is pointing towards the positive direction. And another interesting aspect is that if you excite a wave packet of spin wave, it will contain frequency above the uniform mode, but also below the uniform mode. So if you record a frequency domain spectrum between your two antennas, you will have a signal that will look like an envelope plus an oscillating spin wave signal. But the difference compared to the V-shaped dispersion relation is that now the center of this envelope is at the uniform resonance. What is below comes from negative wave vectors, and what is above comes from positive wave vectors. Okay, but if you don't know where is your uniform mode in frequency, you may not see a difference between this type of spectra and the ones that you would obtain for forward waves or Damon-Eshbar. But in contrast, if you look at the spatial contrast, so you look at the transmission coefficient versus the propagation distance, then you see that because the group velocity is always pointing to the right, this kind of spin wave can only transmit energy to the right side. So if you place your receiving antenna on the left, you expect no signal. While if you place your antenna on the right, you expect a strong spin wave signal. So this is a situation where the transfer of energy by the spin wave packets is truly unidirectional. And you can describe that analytically and make an experimental demonstration. And this is, you can see that in my poster at Magnonics or in the papers of our PhD student Florian. And this brings me to my summary, and there's a few messages I would like you to remember. First, a spin wave can be described as a fringe magnet with stray fields that are very asymmetric depending on where you look at their stray field. Since the spin wave is the analogous of a dynamical fringe magnet, it has two sides, bright side and a dark side. An RF antenna here says the same. Me too, I have a bright side and a dark side. Okay, and the dark side is when the two components of the RF field lead to opposite torques, and the bright side is when they lead to torques that help each other. The good thing about the antenna is that you can play hide and seek with the spin wave by just rotating the antenna so that the dark side is fully black. Another message that I want you to remember is that when you excite spin waves in your system, the spin waves can be slow or fast. And if you want to selectively study the slow or the fast spin wave, you just organize a race by looking at your signal in time domain and time gating your signal and coming back to the frequency domain. And my last message is that the spin waves can have different flavors, especially if you work in multi-layers, and they can be non-reciprocal with either standard dispersion relations or very counterintuitive dispersion relations. And when you have these counterintuitive dispersion relations, then the spin waves are non-conformist. Okay? And they can have their phase that propagates to the left, while their energy propagates to the right, which leads to true unidirectional energy transfer. And this ends my talk, and of course, most of the work I'm doing is made possible by the team of scientists that help me in my everyday research. And so I would like to thank especially my colleagues Tu Van Kim, Claude Chaper, and Jean-Paul Adam, as well as all the postdocs and the PhD students that contributed to this, and external collaborators. And with this, I thank you for your attention.